new recording. So, NoSQL or not only SQL. So, what is the motivation behind these not only SQL systems? So, a traditional relational database has a large overhead. So, there's a combination of strong consistency requirements. You have a powerful query language and also transactions. And those properties of a relational database make it hard to scale horizontally. And so with scaling horizontally, we mean using a cluster of usually not two, but really hundreds of machines, maybe distributed over the world at different data centers, like in the US and in Europe, for these large international internet companies such as Facebook, Google, Yahoo, and so on. What happened was lots of this, it really starts with these big companies. They didn't need complex queries or transactions. So transactions are useful if you have bank transfers or reservations, but that's not always the case. So for example, for Twitter, you have short text messages. They need to be stored and retrieved based on keywords or hashtags or the sender of the tweet. But you don't need joins, you don't need group by queries, you don't need strong transactions. And for tweet, it's not that important. Similarly, for Amazon customers, if they add something to their basket, you don't need transactions. Each user has its own basket, and they can add or remove items. And so for these types of applications, they can live with weaker consistency notions. And so that means it's not like a bank transfer where it's important that the balance is always correct. It's allowed that some data is not entirely up to date or only becomes up to date after some time. For instance, for Twitter, if you send a tweet at 43 minutes after 1, and then there's another user E, and he wants to he clicks on the web page and he wants to see all the tweets of user A. It's at 1 minute later or 2 seconds later, but he doesn't see the latest new tweet, which was added a couple of seconds ago. That's acceptable. So that's a type of weaker consistency. So you don't need the data. It's allowed that the data is a little bit delayed. If there's a couple of seconds delay between storing and then reading new data, that's perfectly acceptable for that case. Also for Facebook, if you post a message and in 0.01% of the cases something gets wrong and the message is maybe not stored, that's also acceptable. Because with a database you have a transaction, and when it's committed, it's always stored. But for Facebook, if you sometimes lose a message, that's still acceptable. Users will just repost a message, and it's not like, again, a bank transfer where you really want that transfer to happen. And then the third case is Amazon. And if you, for instance, remove an item from your shopping cart and Amazon, because of the high load or something, at that moment doesn't do that. So it forgets the action that you clicked on the remove button. That's also acceptable. So these are types of weaker consistency, and the main advantage is if you have weaker consistency, we can have more throughput, so we can handle more users if we do not have to comply with these strong transactional requirements of a traditional relational database. So the NoSQL movement emerged So this is the development of special purpose, highly scalable data source. So highly scalable meaning data is spread over different continents, over hundreds of machines in each continent. So they're highly scalable, and their special purpose, meaning they store a specific type of data, such as tweets or Facebook messages or shopping carts at a retail online retail platform. So this NoSQL movement was inspired by a number of technological developments with Google, Yahoo, Amazon, and so on, because the amount of the volume of data was beyond the capacity of traditional relational databases, and also the traditional way of how software was made. And so it was really a movement that was dictated by this huge amount of volume, this huge amount of web scale interactions with users, and really a lot of different software systems were just not cutting it any longer, and that's where it started. So for databases, what they wanted was simpler data types, simpler queries, weaker notions of transactions and consistency. And the last point is the most important, really systems that scale out, so where it's easy to add one computer to your cluster of thousands of computers, and that you can easily add and remove computers to a cluster. Also in the case of machine failure, those systems were designed to handle machine failure. And I'm going to start now with a couple of presentations, a couple of slides where it all started. And it all started actually with Google. So I don't want to make a lot of advertisement of Google, but Google was really at the center of that early and still these days also of the type of technological innovation is really central to the NoSQL movement. So still in its early days, so that's the beginning of 2000s, Google faced the problem of hard disk failure in their data center. And so their core business is still to provide data, so their search engine. And because a lot of these hard disks were failing, they started actually with replacing low-cost disks with more expensive ones. So makes sense. If your hard disk fail, and that's the main problem in your data centers, you just buy more expensive disks. So what happened? Yeah, the company grew. It's grown a lot since then, and so the total number of disks soon counted in the millions. So if you have 100 expensive disks, the chance that one is going to fail on a certain date is small. But if you have millions of disks, and even with a longer disk life, in that pool of hardware, it was inevitability that a disk will fail again, and almost by the hour, because even if a hard disk has a chance of 1 in a million of failing on a certain day, if you have millions of disks, you can expect one to fail every hour. So this means that the exact same problem as before. So what did they do? They moved back again to normal low-cost disks and solved the problem by considering that a component failure, so a hard disk failure, was not an exception, but just a regular occurrence. And they tackled the problem, and that was the genius of that idea, to design a software system that was able to auto-repair itself. So was able to handle a disk failure as just a normal thing. So in 2003, they solved this problem, and they published a paper on Google File System. So I've shown the link here below. If you have a lot of time, those early Google papers are really interesting. also not that difficult to understand. So the conclusion from the paper, or in the abstract of the paper, they say the system is built from inexpensive commodity components that often fail. The system constantly monitors itself and detects, tolerates, and recovers promptly from component failures on a routine basis. So Google File System was published, and we already saw the open source implementation in week 3 when we discussed Amazon AWS components such as S3, which also are based on Google File System and the Hadoop file system that's now available open source. And so just a little recap, because probably you forgot these slides that I showed you 3 weeks ago, 4 weeks ago already. Is it? So Hadoop file system, how does it work? You have several servers, which are called data nodes, and each data node contains a block of data. And so usually every block is replicated on 3 different servers. So that means if one server crashes or one hard disk crashes, you still have a copy on 2 other servers. And the system works that if you access a file, it goes to available data nodes and gives you back the file. If then one of the data nodes crashes, that's not a problem. You just get referred to another server where the data is on. And if that server then later becomes back online, or if a new server is added, the system will take care to ensure that that block of data is copied, or some blocks of data are copied to the new server. And so that's how it works. And so every data node, so every data server sends a heartbeat every 3 seconds. So if a server crashes at some time, the main server will know after 3 seconds. So that's a bit how it works. And the advantage of this system is that it scales out, so you can have hundreds of computers, hundreds of data nodes. The data is replicated, so it's always safe. And only in the occasion that only if 3 servers crash within 3 seconds, you have a problem. But the chance of that occurring is really low. So in practice, your data is always safe, even if one of the millions of data servers crashes every hour. So that was the first big inventions from Google. It was not only Google, so HDFS was later developed by other people who read that paper of Google and created an open source version of it. Because typically with Google, the actual software, it's always proprietary. And so Google doesn't share the actual implementation of their file system, but at least they shared some insight with that publication. So that was the first main invention of Google. Then they continued. So Google was active with collecting and analyzing high volumes of website data. So you must realize that every day Google has software, and it basically visits all the websites in the entire world. So that's called Google Spider. And so they visit actually every website in the world, and then they store statistics on every web page in the world. Now, if you want to then analyze that amount of volume of websites for optimizing search results, that's extremely difficult. So it's extremely difficult to write programs that run in parallel on thousands of machines at the same time, can process petabytes of data. So that's really difficult. And especially because the engineers had the same problem as before with disks, because if you have programs that process data stored on millions of different machines, then also machine failure is a regular occurrence and not an exception. So what they then published was MapReduce. So MapReduce will also be the main topic in week 8. So MapReduce in essence is to simplify data processing on these large clusters with thousands or millions of servers. So in essence, it's a programming model, and it's also an implementation for processing and generating large data sets. End users, that means the programmers, they specify their algorithms or their programs in terms of map and reduce functions. So that's where the name comes from. We will see that in details in week 8. And the underlying system automatically makes sure that these programs are parallelized across these large clusters of machines. The system also take care of machine failures, and also schedules the communications between the machines to make efficient use of the network and disks. And so it's a nice system. So for programmers, they find the MapReduce programming language easy to use, and using MapReduce, Google processes a total of more than 20 petabytes of data every day. And so 20 petabytes, that means 20,000 gigabytes. So that's really a large amount of data. And I think with a normal computer, you may have like, I don't know, 500 gigabytes of storage these days. So if you're talking about 20 petabytes, yeah, you need at least hundreds of computers. So that was a second problem they solved. And also, so Google published MapReduce, but later on it was developed by other people, and it led to the open source versions that you can use these days. And then a third problem was also similar in nature, for storing data in a database. And again, we have the problem, they have billions of web pages, and each web page has a number of properties. The title of the web page, how many users visited that web page, links to other web pages, and so on. So they want to store those properties in a database, and they also wanted to have a complete history. So they index the web every day or every hour. So they want the history of changes, and maybe the title has changed of a certain web page, and so on. So they also want that history. So that, again, that's petabytes of data. It means it's stored over hundreds and thousands of machines. And so then they published Bigtable. And Bigtable is a distributed storage system for structured data. Again, a paper from 2005. And the main properties of Bigtable are, again, yeah, it's a proprietary implementation. So we don't know actually in detail how it's implemented. You can use it using the Google Cloud Infrastructure as a Service. It's currently used to support Google applications such as web indexing, MapReduce, Google Maps, YouTube, and Gmail. It makes it easy to add or also remove, in the case of machine failure, machines, and automatically take advantage of these large clusters of machines. And then if you look at the data format, you see here's a little visualization. You have different rows. Now for Google, for Bigtable, the number of rows can be in the billions and trillions. So actually the table is split into tablets, they call it. So each tablet is actually a segment of the table split on the row key. So you have a primary key, and they split each table so that each tablet, each partition is only a few gigabytes. So that's how they partition the data, and then you can store these tablets using Google file system, which is similar to Hadoop file system on several computers. So that's one aspect. And then the other aspect is that you don't have traditional columns as you would have in a relational model, but column families. So each column family is actually a set of columns, and you can have an unlimited amount of columns within each family. So that's how it works. And then you also have the time dimension. So you have properties of each row are stored into one or more column families. And then you can also have a different version based on which day the data was updated. So a similar database with an open source design that's then based on the original paper of Google is Apache HBase. So again, a big leap forward within distributed computing and designed to handle that web scale type of data. And then a final example of Google. So in 2010, so a little bit later, they again wanted to do interactive queries on large tables consisting of trillions of records stored in different data sources, and really interactive. So that means results within a couple of seconds. And then they published Dremel. So Dremel is about interactive analysis of web scale data sets. Again, it's a proprietary implementation. It's not, we don't have the code, but it's available as a service, known as Google BigQuery. Again, scalable, and you can use queries only for read-only data, so it's not possible to change the data, but you can query the data for analysis, and it also runs on thousands of CPUs or petabytes, and you can query trillion row tables in seconds. So there in the paper they use a column-based storage representation, and yeah, we saw that in the previous presentation where we talked about also this system in Apache Drill. So Apache Drill is the open source variation of Google BigQuery. So that concludes that small origin story centered around Google. So let's start with an overview of NoSQL systems. So for NoSQL system, or not only SQL systems, are more specialized databases. So there are a couple of different types of systems, and you can categorize them in two orthogonal dimensions. So the first dimension is the type of data they handle. And we saw that in the first week when we talked about file types. And so there are different types of data. You can have graph data or document-oriented data, and so on. So one way to classify NoSQL systems is in the type of data they handle. And then another dimension in which you can classify or categorize NoSQL system is how they trade off performance. So they trade off performance with consistency and also resilience to crashes or network errors. So basically that's a trade-off. You cannot have a system that's both performance and consistent in the sense that it supports transactions and that the same value of a variable is consistent over all the different computers where that value is replicated, and have it resilient in the case that any machine or network problem occurs and some data or some node becomes unavailable. So that's another dimension. And common characteristics of NoSQL compared to a relational database are typically you have a less stringent schema. So the schema is more free. You can have more dynamic number of columns. Typically the query language is a little bit less powerful. So it's you cannot have joins and group bys or something. Some system only allows you to get a document and then save the document, for instance, and you cannot join different documents or something like that. So a little bit less power in the query. Better integration in applications. So we saw some applications like Twitter or the Amazon. How do you say it? The Amazon shopping list, where you add your add your shopping basket, sorry, where you add your products, and Facebook messages. So each application has maybe a special purpose NoSQL database that's suited for that. And last point, but that's extremely important for web scale, is that those systems are highly scalable. So they run not on a single computer, but on a cluster of hundreds or thousands of computers. So we have four types of NoSQL systems, and here we look at the type of data that makes them different. So we have key value stores, and examples are Redis, Amazon DynamoDB, and RIAC. Column-oriented databases, and we already saw Google Cloud Bigtable, Apache HBase, which is the open source version of that, and Cassandra. Document stores such as MongoDB and Couchbase, and this afternoon you will do some exercises on MongoDB as an example, and then finally graph databases using Neo4j, for instance. So let's go over these different variations. So the first type of database, NoSQL database, are key value store. And a key value store is essentially it's a map. It's like a dictionary in Python. You have a key and a value. For instance, here you have user 001, and that's the key. And then the value are, in this case, his name and the age. So a simple property or a small set of properties stored in JSON or something like that. That's what a key value store in essence is. And of course, the difference with a dictionary in Python is that this dictionary stores its data over hundreds of different computers. So it's not that simple. But if you look at the type of data it stores, it's just like a dictionary in Python. So you have atomic set, put, and get operators. So you can add a new value, you can change the value, or you can retrieve the value based on the key. And different key values stores have differences in the data types they support for values. Can be only a string or maybe more complex types of values such as JSON, and also the operations they support. So there's some differences in that. So the key value store doesn't support joins, no range queries, only simple put and get operations. And what are some use cases where a key values database is useful? For example, caching systems. So caching means storing some objects in memory, and then instead of having a server or an application that has to compute that object, you use a cache. So that means storing something temporarily. For example, you can visit a web page, and then if you visit that web page again, 1 second after that, you can retrieve the web page from the cache. So you don't have to go back to the server and retrieve it again. So that's kind of a use case for key value stores. Another use case are user profiles. For example, LinkedIn or Facebook, you have your profile with some data associated, like your current job or your degrees you had. So there the key is just your user identifier, and then the value is all the data for your user profile. And then the third use case is web statistics. And then here the key is the page, the URL of the web page, for instance. And then the value is the number of times the page is visited. So often if you have your own web page, you want to have statistics, how many times the web page was visited. That's also something you can store in a key value store. An example is Redis. So it's a key value database. It has an expire property. So expire means if you, for instance, if I store my user profile and I can let it expire in 1 day. That means Redis has my user profile. But if I upload it to Redis and I wait 1 day, it expires. So then Redis has to again fetch my profile. And so that's to make it suitable as a caching system. So it doesn't matter if my profile that is then updated the next hour or 2 hours after that, users still get my old profile. But that's okay for some application, and you can set the expire date as you want. So you can let it expire in 5 seconds or 1 day. That's an option. Another property is that it works like a message broker. So that's like a linked list data type with blocking reads. And what that means with the message broker and also with publish subscribe is if you have at the same time millions of requests to read something, then Redis creates kind of a queue. So instead of an immediate answer, all the requests for that type of information are scheduled in a queue. And that makes the system also more scalable, because if you have like a really high traffic peak at 1 minute or seconds, then the system might break down if it wants to immediately give an answer for all these queries. So that's why you need some kind of buffering going on, and that's what a message broker in essence provides. So Redis is used by Twitter. And here's a quote from Twitter, because most of these internet companies are quite transparent in the type of technology they use or indeed develop. So Redis drives the Twitter timeline, and a timeline is an index of tweets indexed by an ID. And you have this, and these are stored in Redis, and you can together that those types of tweets then produce a timeline. So that's how Twitter actually uses Reddit. Then the second type of NoSQL systems is a document database. So we already saw what documents are. So documents are a string textual representation of some data, either in XML or JSON format, and each document can have its own structure. Some examples again in JSON. So here first name, last name, age, address, phone number, and so on. So this can be a user profile. And here you have the same example, the same type data, but stored in XML. So that's a different syntax. And a document database is just that. It stores millions and millions of documents. Each documents have their own structure. They're all represented in either XML or JSON. And yeah, it's a little bit more transparent than a value in a key store. So in a key value store, you usually have a simpler type of value. And with the document oriented database, it's also possible to retrieve parts of the document. So if you have all these user profiles and you just want the user names, that's also possible with a document type database. Often also some type of search capability is built in, so that you can search all documents efficiently. So that's with a kind of inverted index we also saw in the lab session during the algorithms and data structure presentation. And so important is there's no fixed schema. It's still possible to add a schema. For example, for XML, there are you have XML schema, and then you can check that each document is in a certain format. But you have the flexibility at least to add new tags in XML or in JSON, add new properties how you want actually. So, and then the third type of database is a column-oriented data store. So here that's slightly more complicated than a document database. So here you have every you have rows. So again, the notion of rows. Each row has a unique identifier, but then instead of a couple of columns, you have column families. So every column family is linked to some high-level concept. For example, you can have all the columns which are personal about your customers. Then you can have columns about maybe the profile of your customers, and then maybe you have columns about purchases that every customer has made. And so these are 3 types of column families, and within the column family personal, for instance, in this case you have 2 columns, but it can be an unlimited amount of columns. And also the tables may be sparsely filled, so that means that for some columns you only have a couple of values that are actually filled in, and that you have a lot of null or empty values. And sometimes they also offer versioning out of the box. So for example, Google Big Table and Apache HBase, they also allow you to have different versions of the data. And so if you, for instance, have a user profile and you change the name or the age of John to 26, then you still store the previous version of that data. And so you really have a timeline, and every time you change the data, you keep a backup, if you want, of the complete history of those values. So that's also something that's supported often. So why column values? Column families. So in essence, key value document store column-oriented databases, they are all variations of aggregation-based data sets. So the aggregation level is a unit of data. We like to think of it as one object. So for a key value, it's the value. For documents store, it's a document. In column-oriented databases, it's the column family and also the row. So these are 2 dimensions. But we aggregate all data related to the same object in one place. And by keeping those objects together, we improve the performance because we don't have to join different tables. So in a relational data model, you always have to join. And also, if you distribute the data, so if you store it in different servers, then you can keep data within objects, those values together. So which is also more efficient if you scale out or scale horizontally. And then the final type of databases are graph databases. So these are a little bit the odd one out in the NoSQL landscape, because here the data is represented as a graph. And so every row, you don't really have the concept of row, everything's an object connected by relations. And so that's how it works. Every node is really an instance of one user with a number of properties and then linked to other users using different relations. So it's a little bit special, graph databases. Okay, that concludes the overview of different NoSQL systems. And so in essence, we categorize them on the first dimension, and it's the type of data they store. But then now we're going to look at the technical dimensions, and we're talking a little bit about sharding and replication. So in a NoSQL database, there's a trade-off. And it's based on 2 principles. So if you want to increase the availability of services, we need to distribute data. There are 2 techniques here: sharding or partitioning, and replication. So sharding or partitioning, that means, we'll see what it means, but it means in essence to split the data or partition the data and keep a part of the data on a different server, and replication means copying the data on the same data on different servers. So those are two strategies to distribute data. However, when you start with distributing data and also computation, there are some challenges, and the main challenge is consistency. If you're going to copy 2 copies of the same data to 2 servers, and then it changes on one server, you have to make sure that on the other server, you have to update that copy. And then you have the CAP theorem. So the CAP theorem is really central to these NoSQL types of systems, and it's not a theorem in the theoretical sense. It's more of an observation, but the observation is that if you have a database system that is distributed, you can have at most 2 of the following 3 properties, and that's CAP. So either you have consistency and availability, or availability and partition tolerance, or consistency and partition tolerance. So you really have to pick 2 out of those 3 properties. And it's also useful because you can use that observation to classify the different NoSQL databases. And so you have to be a little bit careful, because in practice, most of the systems we saw allow to configure trade-offs. And for example, with settings and parameters, you can control the trade-off between consistency and availability. So what is consistency? Consistency is that the client always has the same view of the data. So that's basically comes down to transactions, where you do a bank transfer, and if you do a transfer over 5 different databases, that means you're going to write the same data to all 5 systems, and only if all 5 systems commits, then the data is considered to be saved correctly. And so that's really consistency. So if you have a highly consistent system, that means if you're going to read some data, it will always be going to be the same value. If you ask it to server 1 or 5, they will all return the exact same answer. So that's strong consistency. And then availability is that clients can always read and write. So that's a different property, highly available. So that means that you can also always read some data, and that doesn't take a lot of time. So that's also important. So one method to ensure high availability is just to copy data on every server. If you have the same data copied on every server, it can be a server in the US and one in Europe, then you're always sure that you can have your data back quickly. And even if a server crashes because it's copied on another server, you still have that data. So those are highly available systems. And what you typically have with databases, relational databases, like MySQL, is you have high availability and high consistency. But then you have the third requirement for a system, and that's partition tolerance. And that's a property that means that the system works well despite physical errors. So infinite scale out, they call it. So even if a machine fails, that the system, that the cluster still works properly. And that's something you don't have with databases. In databases, if one server fails, that means you cannot longer write all data in a consistent way, because the one you're waiting on that one server that is temporarily shut down or rebooting or has a machine failure. So you really have to choose. And so with the CAP theorem, that means you can choose 2 out of 3 properties. So you cannot have everything. Okay. And then sharding applications. So in order to increase the availability of service, we need to distribute data, and so the main thing is replication. So here we have table, a key value table, ID and name. And if you want to make it highly available so that everyone can always read that table in a fast way, and you have millions of users want to access the same data, then you just copy that data over different servers. So in that way, even if you have millions of users at the same time, if you have enough computers and the data is replicated, every user can always access that data. So that's one way to design a system. And then another thing is sharding. So here we have the table from before, but now it splits. So here the first two rows are stored only on node A, the second two rows are stored on node B, and the last row is stored on node C. So that's sharding or partitioning the data over multiple nodes. And of course, that's also important. If you have terabytes or petabytes of data, yeah, it's physically impossible to store it all on one server because you don't have enough capacity. So sharding is also important, like with Facebook. You have literally billions of users, I think. So that database cannot be stored on one computer. So you're going to partition it over different computers. So both techniques, principal techniques, have their own advantages and disadvantages. If you look at sharding or partitioning, well, a main benefit is that it scales well with the data size. If you have bytes of data, but if you just partition it into chunks and store chunks each on a different computer, then it scales really well with the size of the data. And so for replication, you have the opposite. If you want to copy data to every node, that's a problem, because if it's too much data, you cannot copy to every node. And then the second property, with partitioning, you have increased parallelism, because, well, different computers store a subset of the data, so you can process data in parallel. So while with replication, there's a problem because you need some kind of synchronization. If the data needs to be updated, you have to update all copies. So you need some kind of synchronization. And then the disadvantages of partitioning or sharding are that if your query requires data spread or partitioned over different nodes, you have some overheads. While with replication, if all nodes have all data, yeah, you can do a complex query because all data is on a single machine, so you don't have that overhead. With replication, you need a way to locate a data item, which is not necessary for replicating. When replicating, with partitioning, there's a problem because if one node fails, that means some segment of the data is no longer available. While with replication, yeah, if your data is on every machine, it's resilient to crashes. You just go to a different server that has the data. And finally, if your data is partitioned, you can have problems with load imbalance. So load imbalance means that all users are interested in the same data. So they all go to the same nodes. But yeah, then you have a problem with the capacity of that node. So the load is not balanced. And so with replication, with replicated data, it's easy to balance the load, because if you have millions of users who want to access a certain row, you can just distribute them over all nodes because the data is replicated. And so this is in a nutshell like the pros and cons of partitioning and replication. And that's usually, it's a logical conclusion. So all these systems, what they actually do is they use a combination of sharding and replication. So that means they combine the strengths and weaknesses of both approaches, and they do a mixed, they offer like a mixed type of service. So here's an example. Again, we have our table with 5 rows, and you see like Jan Veerle, the first 2 rows. the data is partitioned, so we don't store all the data on a single node, which is good because it wouldn't fit. But we do, so it's a combination. So Jan Veerle, it's duplicated on 2 servers, not on all servers, but on 2 servers. Also Jeff and Elaine, so that data is replicated, but it's also partitioned. So it's a mix of both approaches. And what you get is higher availability. You get fault tolerance. So if your machine crashes, it's not too bad because the data is replicated at least on one other machine. You can better balance the loads. So if there are millions of requests for Jan Veerle, they can go to either node A or B. And it's also less time to synchronize data than if you would replicate all data on all nodes. And so if Jan and Veerle changes, you also have to change it in node B, but not in node C. And so that combination of partition and replication is used in practice by all systems. We dealt with the issue that distribution of data across several servers comes with a number of challenges. And so these systems have to deal with the fact that a node can disappear. A server can always crash, can be out of memory, or can be a physical failure, like there's no power supply or the hard disk crashes or something like that. Also related, a node can disappear, but you can also add new servers. Also important, you have to ensure consistency among replicated data. You also have to figure out where the data is stored. If the data is partitioned, then you have to first identify on which nodes it is stored. And you also have to need to be able to handle complex queries that combine data from different servers and so on. And so there are a number of challenges and also some trade-offs. So we cannot get all of those functions. So that's why NoSQL systems are also limited in scope, because you cannot provide everything as shown by the CAP theorem. Okay, so that concludes my second presentation. I have some additional information here about the CAP theorem, but that's something you can study in your own time if you're interested, just to provide some additional details. Are there any questions? Was it a little bit clear this week? Because it's a difficult topic. Am I going too fast, too slow? Any questions? Clear to me. Okay, thank you, Björn. Very good speed. Okay. Okay, that's good. Thank you. Thank you very much. Nice to hear that it's going well with this Corona times and this online teaching. It's difficult sometimes to assess if it's all clear. Okay, fine. Yeah, I think our time is up. Unless there are any final questions. No? Okay. See you next week. Bye.